Hello students, welcome to series of lectures on digital speech processing. So in this video you will be able to learn a classroom discussion topic on LPC analysis, that is autocorrelation method. So in the previous videos we have already introduced what is LPC analysis, what is the basic principle of LPC, and we have also seen that how we need to estimate the prediction coefficient. So to estimate the prediction coefficient, what are the issues that we may come across, okay, and how we need to solve those issues, okay. And we have already seen that, so with the help of the two methods we can easily solve the prediction coefficients. One is autocorrelation method and the second one is the covariance method, okay. So now in the next video we can see that covariance method, but in this video you will be able to learn what is a autocorrelation method based on LPC. So let's get started. Right, so this is some of the introduction part of linear predictive coding that we have already seen. The basic idea, the current speed sample can be closely approximated as a linear combination of the past sample. So this is the estimation sequence of the speech, that is S of n equal to summation alpha k into S of n minus k. So this alpha k is our objective, okay, so that we need to estimate effectively. So these are the method covariance and autocorrelation. First let us start with our autocorrelation method and then we can move on to the next method as the covariance. So the solution for alpha k also we have already seen in the previous video. So in the previous video we have clearly mentioned that to minimize the mean square prediction error. So actually we can call this as the MMSE only, that is minimized mean square error. But particularly speaking, actually this is minimum mean square prediction error, because you are going to be predicting the speech current sample, right? So there you'll be having some kind of error that is producing, okay. So that error I'm calling as a prediction error. So that we need to minimize. So what is the procedure that we have already adopted to minimize that? We have given what? The first derivative of the energy component of an error with respect to alpha I is equals to 0. So by setting this equation equal to 0, we'll be having the set of p equation that can be available, because I is varying from 1 to p, okay. So leading to a set of p equations in p unknowns, and that can be solved in an efficient manner for alpha k, okay. This we have already seen, and the process also I clearly explained about this. So first we need to compute the phi n of I comma k for I is varying from 1 to p, and we need to solve the matrix equation for alpha k, and we need to specify the range of m to compute phi n of I k. That is the biggest challenge actually, because we need to estimate the prediction coefficient directly from the speech, okay. That means whatever the summation that they are going to be seeing from the slide, En, the first equation, so En is equals to summation of m. So this is the infinite length of the m that we are considering, but when it comes to efficient manner how we are going to be computing the prediction coefficient, so we need to fix this interval. So in order to fix this interval of the summation, we are going to be choosing the methods, okay. So we need to specify the range of m to compute the phi n of I comma k, okay. So the first method we are seeing today is the autocorrelation method. So this is a matrix form, this is a p by p cross p matrix, and these are the column matrices. So these two are the column matrix, and this is the p cross p matrix. Right, so what is the basic idea of the linear predictive coding that we already know, okay. So how the current sample is closely approximated to the previous past samples. So that is the way we have represented in the mathematical equation as S of n is equals to summation where k equal to 1 to p. The k is taking the values from 1 to p, alpha k into S of n minus k. That's all. So the current speed sample can be closely approximated as a linear combination of the past samples. Now, so when it comes to the autocorrelation method, we already know the basic representation how the autocorrelation function that can be possible. Okay, so let Sn of m which exists within a length of the sequence, but means what you are going to be doing, you are applying the window technique. Okay, you are applying window to the corresponding speed signal, and that is the reason we have taken the window length, that is 0 to L minus 1. So what is the reason for choosing the autocorrelation method is that we are going to be fixing the interval of the summation, because in order to compute phi n of I comma k, that is a p cross p matrix, so to compute the phi n of I comma k, first we need to know what is the limits it is going to be taking, who is going to be taking the summation. Okay, so this is the way how we are going to be fixing the interval length. So this Sn of m is nothing but S of m into W of m. Okay, it is a windowed speech we can call. This is the WS, windowed speech. Sn of m equal to S of m into W of m, where S of m is the actual speed signal that we have already recorded for a time axis on a time frame of 5 seconds or 4 seconds. Then you are applying window of a length of 20 milliseconds for instance. So many frames you are going to be taking, but among those we have taken, so this is the autocorrelation method. So this is the rectangular window for instance, from m equal to 0 to L minus 1. Okay, now so what you need to understand, there is a signal within the limits of 0 to L minus 1 and the speed signal is 0. So here the speed signal is 0 outside of the limits of the window, so that we need to estimate. For instance, what is the issue here? Okay, what issue we are going to be having? For instance, if you want to what is LPC? The basic idea of LPC is nothing but we are going to be estimating the current sample with the helping of the previous samples data. Okay, so let me take, this is my first sample. Okay, this is my first sample. So to estimate the current sample or the first sample of this window, then we are collecting the data from the previous samples. But unfortunately, what is happening here, outside of the band, outside of the region of our interest, their samples are 0. Then we are going to be taking all the samples, and if you want to draw the graph of the error sequence and the large error that can be possible here. Okay, the point is very clear, because the basic idea of the LPC is that we need to estimate the current sample with the helping of the previous past sample. But in this case, the previous past samples are all zeros. But to estimate the current samples, we will be having large errors. But what is our agenda? We need to minimize the error, right? But during this, what is happening? We are going to be getting the maximum errors that can be possible at the beginning of the window. And similarly, at the end of the window also, you will be getting the maximum error that can be possible. That is the biggest drawback of this autocorrelation method. Of course, there is a solution is there. So in that solution, we are going to be introducing the Levinson-Durbin algorithm. Okay, so to overcome the problem of this, that we can see in the further videos. Alright, the same thing whatever I have mentioned in the previous slide, I have given in this, So at values of m near 0, we are predicting the signal from 0 value samples outside the window range. So therefore, the error sequence will be very large. That point we have already seen. And at values near m equal to L, that is at the end of the window, so we are predicting 0 valued samples outside window from non-zero samples. So En cap of m will be relatively large. So for these reasons, normally use windows that taper the segment to 0. That is the example of the Hamming window. Now let us see the pictorial representation of that also, so that you can easily understand. Alright, so these are the pictorial representation. When you apply the Hamming window like this, we are going to be minimizing that, because we need to taper the segmentation of the speech signal. Now when you apply the Hamming window like this, okay, then this is a windowed speech signal, because within our interest of the band only we are considering from 0 to L minus 1. And the error sequence that also we are going to be estimating, like Sn of m minus prediction. This is actual speed signal, and this is the prediction speed signal. Okay, so the error will be minimum if you want to reduce the difference between these two. Okay, but unfortunately at this portion the errors are very high, and at this portion also the errors are very high. The large errors we are going to be seeing at the beginning and ending of the window. The same thing when you take the samples also, when you take the rectangular window, the same procedure. This is the Rn of k. Okay, now we are going to be representing this Rn of k in terms of the pi n of I comma k, because to compute that we are going to be estimating the prediction coefficient values from alpha 1, alpha 2, alpha 3 to alpha p, because I is varying from 1 to p, right? So those prediction coefficients, in order to compute the values, first we need to understand what is the matrix phi n of I comma k. So to compute the phi n of I comma k, we need to represent this autocorrelation equation in terms of phi n of I comma k. This is the large errors at the windows of at ends of the window, here and here. Alright, so this is the way how we are going to be representing phi n of I comma k. So phi n of I comma k nothing but this we already know. So in terms of Rn of I minus k. Okay, so wherever you see phi n of I comma k, in place of that I am substituting Rn of I minus k. That's all. So this is the Rn of k signal, that autocorrelation signal. Okay, the actual signal multiplied with the delayed by k samples. That is the normal definition of the autocorrelation. So this is the way how we are going to be representing. So alpha k into Rn of I minus k equal to Rn of I, and the error signal is also we are representing in terms of Rn of. Now if you want to write the matrix form, that is Rn of 0, 1, 2 and up to p, because I is taking from 1 to p, and we'll be getting alpha k is the column matrix, and this is the Rn of I minus 0, that is 1 minus 1, 1 minus 2, 1 minus 3, like that we can see in the next slide. So this is the P cross P matrix, and this is a column matrix, this is also column matrix. So this I am calling, the whole matrix I am calling representing as a capital R. This is alpha, this is small r. But what is our agenda? We need to compute the value of alpha, right? So by using the simple matrix inversion also we can possible, that is alpha equal to R inverse R. But when you observe carefully this matrix, all the diagonal elements are same. Okay, so that is why R is a P cross P Toeplitz matrix. So the Toeplitz matrix is nothing but which is symmetric with all diagonal elements are equal. Okay, this is simple, and but it is very complex actually. When you want to apply the matrix inversion, it is very complex. So what is the solution? Now, when you ask what is the solution to compute the values of alpha 1, alpha 2 and so on alpha p, there is one more algorithm we are going to be introducing, that is Levinson-Durbin algorithm, that we can see in the further classes. Thank you students, thank you for watching this video.